I'm Tim. This PCB Sync.
This episode is a set of 10 topics aimed at engineers. We'll use official materials from Rugged and a 5.8G open source RF PCB project to clearly explain R4350B's Stackup, impedance, drilling, via metallization, hybrid lamination, and surface finishing. If your project is about to go into production, it's best to clarify these issues before exporting the Gerber files. Let's start with the Stackup. The standard thickness R4350B has a dielectric constant of 3.48 plus or minus 0.05. However, when it comes to transmission line dimensions and electrical length, Rugged provided a design dielectric constant of 3.66 for this simulation, so when calculating impedance, you can't just use 3.48 for all models. A more reliable approach is to first use the design DK to build the initial model and then confirm the final dimensions based on the actual board thickness, copper thickness, and manufacturing compensation used by the PCB manufacturer. Also, keep in mind that the manufactured DK for 4mm thick R4350B is 3.43, with a tolerance of plus or minus 0.05, so you must confirm the exact thickness before starting the design. Let's take a look at this example of a 5.8 GHz open source branch type imager. J2 is the RF input, J1 is the RF output, and J3 is for bias control. The TL1 to TL4 transmission line structures in the middle, their width affects impedance while their length affects electrical length and phase. High-frequency impedance control isn't just about writing 50 ohms. The design files must also clearly specify the routing layer, reference layer, dielectric thickness, finished copper thickness, transmission line structure, and the allowed tolerances. Despite identical theoretical calculations, variations in etching compensation, dielectric thickness, and final copper thickness can cause impedance deviations. So, the solver can only provide an initial value. Before mass production, the PCB manufacturer still needs to recalculate based on the actual Stackup. R4350B is compatible with many common FR4 manufacturing processes. The Rugged Processing Guide states that it can use the common FR4 developing, etching, and stripping systems, but the drilling parameters cannot be copied directly from FR4. It is recommended to use standard alloy drill bits with a suggested surface speed of 300 to 500 meters per minute. A typical reference value for tool life is 2,000 to 3,000 drill holes. Because the material contains ceramic components, drill bit wear may occur more quickly. In practice, tool replacement should be determined based on the quality of the metallized via hole walls. For metallized vias, R4350B does not require any special treatment before metallization and is compatible with both electroless copper and direct metallization processes. R4350 can be used in multi-layer and hybrid dielectric structures. But when designing hybrid laminates, you can't just consider the electrical properties. You also need to confirm the lamination temperature, value system, dielectric thickness, tolerances, and differences in expansion for the different materials. The CTE of Rugged R4350B is 10, 12, and 32 parts per million per degree Celsius in the X, Y, and Z directions respectively. For thickness, board thickness, high aspect ratio vias, and structures that undergo multiple laminations, it's especially important to check how Z-axis expansion affects via reliability. In terms of surface finish, the official guidelines state that R4350B is compatible with OSP, HSL, and a variety of chemical deposition or electroplated surface treatments. You can't simply assume that a deposited finish is always better for RF boards. The thickness, flatness, and additional conductor loss from the surface finish can all impact high-frequency performance. Ultimately, you need to choose based on frequency, soldering requirements, storage period, and cost. There are 5 main common mistakes in the design of R4350B. The first is using 3.48 to calculate all transmission lines, without distinguishing between the manufactured decay and the design decay. Second, when changing materials or board thickness, only the line width is adjusted, but the electrical length and phase are not rechecked. Third, the impedance requirement is set to 50 ohms, but no reference layer, dielectric thickness, copper thickness, or tolerances are provided. Fourth, thinking that the manufacturing process is similar to FR4, so the drilling and etching compensation parameters for FR4 are copied directly. Fifth, in hybrid stack-up designs, only the decay is considered, without confirming the hybrid conditions, CTE, or via copper reliability in advance. These issues, if discovered through interlayer evaluation and DFM review before production, have the lowest cost to fix. To sum up, rugged R4350B can indeed use many processing steps similar to FR4, but the challenges of high-frequency boards still lie in stack-up, impedance, dimensional compensation, and supply consistency. By using the correct design decay during the design phase and confirming the actual material thickness, finished copper thickness, impedance tolerance, and processing compensation before production, you can reduce the risk of impedance deviation or frequency shift during the first prototype run. If you were designing an R4350B high-frequency PCB, PCB Seam can assist with stack-up evaluation, impedance calculation, DFM review, prototyping, and mass production. Scan the QR code on the screen and upload your Gerber files to start a quote. If you found this episode helpful, feel free to hit the